Event Report: Advancements in Quantum Computing with the Introduction of 4D Error Correction Codes. Date: June 19, 2025. Location: Online announcement via social media platforms. Keywords: Quantum Computing 4D Codes Error Correction Microsoft Atom Computing Utility Scale Quantum Computing. Overview. On June 19, 2025, Satya Nadella, CEO of Microsoft, announced a groundbreaking advancement in quantum computing through a tweet that has garnered significant attention. The announcement detailed the introduction of innovative four-dimensional 4D geometric error correction codes which promise to reduce error rates in quantum systems by an unprecedented factor of 1.000. This development represents a crucial step toward making quantum computing reliable and scalable for practical applications across various industries. Key highlights of the announcement. 1. For 4D geometric codes, the core of the announcement was the introduction of 4D error correction codes. These codes are designed to improve the reliability of quantum computations by efficiently distributing quantum information across multiple dimensions. This innovative approach significantly mitigates the impact of logical qubit errors, which are a major hurdle in the pursuit of reliable quantum computing. 2. Scalability and integration. The newly introduced 4D codes are seamlessly integrated into Microsoft's Quantum Development Kit and Azure Quantum platforms. This integration is a strategic move to enhance the scalability of quantum systems, making it easier to develop and deploy quantum applications in real-world scenarios. 3. Real-world applications. Nadella emphasized that advancements in quantum computing are not merely theoretical but have profound implications across various sectors. Industries such as medicine, logistics, artificial intelligence, and cryptography stand to benefit significantly from the enhanced capabilities offered by reliable quantum computing. Detailed analysis of the 4D codes. Josh Cook, a Microsoft MVP and commentator on the announcement, provided a deeper analysis of the mechanics and significance of the 4D error correction codes. According to Cook, the introduction of these codes is a transformational leap in quantum computing technology, drastically reducing error rates and making computations more accurate. The reduction in logical qubit errors by approximately 1,000 times positions quantum systems to transition from experimental stages to practical utility-scale solutions. Timeline of events. June 19, 2025, the day of the announcement marked a pivotal moment in the field of quantum computing, with widespread recognition of the importance of error correction and hardware advancements in achieving reliable quantum systems. Nadella's tweet not only highlighted the technological breakthrough but also reinforced Microsoft's ongoing commitment to leading in quantum technology development. Implications for the future. The integration of 4D error correction codes is expected to pave the way for practical applications of quantum computing in everyday life. As these technologies mature, they have the potential to unlock new possibilities in complex computations, enabling innovations that could transform industries. The collaboration with Atom Computing further enhances Microsoft's capability to deliver scalable quantum solutions, marking a significant milestone in the journey toward utility-scale quantum computing. Conclusion. The announcement of the 4D error correction codes represents a critical advancement in the quest for reliable quantum computing. By addressing key challenges in error rates and system scalability, Microsoft is laying the groundwork for a future where quantum technologies can be harnessed for practical transformative applications across multiple sectors. As the field continues to evolve, the implications of these advancements will be far-reaching, making quantum computing a central pillar of technological progress in the coming years. The text presents significant advancements in quantum computing, particularly highlighting Microsoft's introduction of four-dimensional 4D error correction codes. While this information appears straightforward, several counterintuitive elements emerge when considering the implications and context of these advancements. Counterintuitive insights. 1. Error correction versus hardware improvements. It may seem logical to assume that advancements in quantum computing would primarily stem from hardware improvements. However, the text emphasizes that reliable quantum computing relies just as heavily on error correction methods. This prioritization of software-level solutions like the introduction of 4D codes over hardware innovations challenges the conventional wisdom that physical components are the most critical for technological advancement. 2. Magnitude of error reduction. The claim of reducing error rates by 1,000 times can be perceived as an incremental improvement, yet it fundamentally transforms the operational capabilities of quantum systems. This dramatic reduction illustrates that even small-scale changes in error rates can lead to significant enhancements in performance and reliability, contradicting the assumption that substantial improvements require equally substantial innovations. 3. Utility-scale quantum computing. The concept of utility-scale quantum computing may initially seem unattainable given the current limitations of quantum technology. However, the integration of sophisticated error correction codes like the 4D code suggests that we are closer to practical applications than previously thought. This indicates that the barriers to quantum computing's utility might be more about overcoming theoretical and algorithmic challenges than technological limitations. 4. Real-world applications. While it is easy to view quantum computing as a niche field primarily relevant to theoretical physics and specialized industries, the text emphasizes its potential for vast applications in everyday sectors such as medicine, logistics, and artificial intelligence. This broad applicability challenges the perception that quantum computing will remain confined to academic or highly specialized uses for the foreseeable future. 5. Collaborative development. The partnership with Atom Computing may seem like a standard collaborative effort, however, it points to a larger trend in the quantum computing field where joint ventures across companies and disciplines are essential. This suggests that the complexity of quantum systems necessitates a collective approach to problem solving, which is contrary to the typical competitive nature of technology development. 6. Holistic progress. The assertion that progress must occur across the full stack might imply that all components of quantum technology need to evolve simultaneously. This is counterintuitive because it suggests that advancements in one area like error correction can have outsized impacts on the overall system performance, reducing the need for parallel advancements in other areas. It challenges the notion that all layers of technology must progress at a similar pace to achieve breakthroughs. 7. The role of software in quantum computing. Traditionally, hardware has been viewed as the backbone of computing. The emphasis on software advancements, particularly in error correction, highlights a paradigm shift where software innovations can significantly influence computational capabilities. This indicates that for quantum computing, the algorithms and codes driving performance might be as crucial, if not more so, than the physical qubits themselves. 8. Perception of quantum readiness. The announcement positions quantum computing as being on the brink of widespread applicability, which may contrast with public perception that quantum technology is still many years away from practical use. This optimism might be counterintuitive given the historical challenges faced in the field, suggesting a shift in narrative that could accelerate investment and interest in quantum solutions. Conclusion. The advancements in quantum computing, particularly through the development of 4D geometric error correction codes, reveal several counterintuitive insights that challenge existing assumptions about the nature and future of quantum technology. By prioritizing error correction alongside hardware improvements, emphasizing the potential for real-world applications, and highlighting the importance of collaborative efforts, the narrative surrounding quantum computing is evolving. This evolution suggests that the path to practical quantum applications may be more accessible than previously imagined, opening doors for innovation across various sectors. The report highlights recent advancements in quantum computing, particularly focusing on Microsoft's introduction of four-dimensional 4D geometric error correction codes and the collaborative efforts with Atom Computing. While the key points are commendable, certain elements may be overlooked. which are crucial for understanding the broader implications of these advancements. Important overlooked content. 1. The significance of 4D codes beyond error correction. Many readers might focus solely on the impressive figure of a 1000x reduction in error rates without fully grasping the underlying mechanics and broader significance of 4D codes. The 4D codes represent not just a method of error correction but a paradigm shift in how quantum information is encoded and processed. This shift allows for more efficient distribution of quantum information across multiple qubits, which can lead to more robust quantum algorithms that can handle complex computations, potentially unlocking new applications in various fields. 2. Integration with existing platforms. The integration of 4D codes into Microsoft's Quantum Development Kit and Azure Quantum is another critical aspect that might be underappreciated. This integration suggests that the advancements are not isolated innovations but are designed to be part of a broader ecosystem. By embedding these codes into widely used quantum programming frameworks, Microsoft is facilitating a smoother transition for developers and researchers into practical quantum computing applications. This could lead to an accelerated adoption of quantum technologies across industries, which is often overlooked when discussing technological advancements in isolation. 3. The collaborative effort with atom computing. The partnership with atom computing is significant for several reasons. Firstly, it emphasizes the importance of collaboration in the field of quantum computing, where interdisciplinary approaches and shared expertise can lead to more rapid advancements. Secondly, such collaborations can foster a competitive environment that drives innovation. Readers may overlook the potential this partnership has to create a more robust and diverse quantum ecosystem, which is crucial for addressing the various technical challenges that still remain in quantum computing. 4. Real-world implications on industry applications. While the report mentions potential applications in fields like medicine, logistics, artificial intelligence, and cryptography, the specifics of these applications are often glossed over. The ability to perform complex calculations at unprecedented speeds could revolutionize drug discovery, optimize supply chains, enhance machine learning algorithms, and fortify cybersecurity measures. Each of these areas has significant societal implications, yet the report does not delve deeply into how quantum computing might transform these sectors, which is a missed opportunity for readers to appreciate the full scope of the technology's impact. 5. Scalability challenges. The report brushes over the significant challenges that still exist in scaling quantum computing technologies despite the advancements in error correction. While 4D codes are a leap forward, the report does not address the remaining barriers in hardware scalability, qubit coherence times, and the overall architecture required for utility-scale quantum systems. Understanding these challenges is crucial for stakeholders to gauge the timeframe and investment necessary for realizing practical quantum computing solutions. 6. The broader context of quantum computing evolution. The current advancements in quantum error correction should be viewed in the context of the historical evolution of quantum computing. The field has seen numerous breakthroughs, but many have not led to practical applications due to various limitations. Readers may overlook the significance of this moment as a culmination of decades of research and development. Recognizing the incremental nature of scientific progress can help stakeholders appreciate the importance of current innovations and maintain a realistic perspective on future developments. Significance of overlooked content. Each of these overlooked aspects has profound implications for the understanding and future of quantum computing. The integration of advanced error correction methods like 4D codes into existing frameworks signifies a move towards practical applications and broader accessibility. The collaborative efforts highlight the necessity of teamwork in overcoming the complex challenges of quantum technology. Moreover, understanding the real-world implications and remaining challenges provides a clearer picture of the current landscape and future directions. By acknowledging these nuances, Stakeholders, from researchers and developers to investors and policymakers, can make more informed decisions regarding the direction of their efforts and investments in quantum technologies. Emphasizing the broader implications of these advancements will also foster a greater public understanding of quantum computing's potential impact on society, encouraging more interest and involvement in the field. 1. 4D geometric codes. The introduction of four-dimensional 4D geometric error correction codes represents a groundbreaking advancement in quantum computing. These codes allow for a substantial reduction in error rates up to 1,000 times by enhancing the reliability of quantum systems through better distribution of quantum information. This is crucial because error rates have been a significant barrier to the practical application of quantum computing. By improving the accuracy and dependability of quantum computations, 4D codes pave the way for more reliable quantum systems that can handle complex calculations essential for real-world applications. 2. Integration with existing platforms. The 4D codes are not just an isolated innovation, they are integrated into Microsoft's Quantum Development Kit and Azure quantum platforms. This integration is vital for scaling quantum systems and making them more accessible for developers and researchers. By embedding these codes into existing frameworks, Microsoft is ensuring that the advancements in quantum error correction can be leveraged effectively across various sectors. This integration is crucial for transitioning quantum computing from experimental stages to practical utility-scale applications. 3. Real-world applications and impact. The implications of reliable quantum computing extend far beyond theoretical constructs. With advancements like the 4D codes, industries such as medicine, logistics, artificial intelligence, and cryptography stand to benefit immensely. For instance, quantum computing could revolutionize drug discovery processes, optimize supply chain logistics through complex simulations, enhance machine learning algorithms, and strengthen cryptographic methods. The ability to perform complex computations reliably can lead to groundbreaking solutions in these fields, making the pursuit of quantum technologies not just an academic endeavor but a practical necessity for future innovations. 4. Holistic progress across the quantum stack. The emphasis on the need for comprehensive advancements across the entire quantum stack, from error correction to hardware, is a critical point to consider. Reliable quantum computing requires improvements in all areas, including physical qubit design, error correction methods, and system integration. The collaboration between Microsoft and Atom Computing to co-design quantum systems highlights the importance of teamwork and interdisciplinary approaches in achieving these goals. As the field of quantum computing evolves, the synergistic development of hardware and software will be essential for overcoming existing challenges and realizing the full potential of quantum technologies. In summary, the focus on 4D geometric codes, their integration into existing platforms, their potential real-world applications, and the necessity for holistic advancements across the quantum stack encapsulate the current state and future direction of quantum computing. These points not only highlight the technical innovations but also underscore the transformative potential of quantum technologies in various domains. 1. The development of the transistor. 1947, the invention of the transistor by John Bardeen, Walter Brattain, and William Shockley at Bell Labs marked a monumental shift in electronics and computing. This innovation was crucial for the development of modern computing as it allowed for miniaturization, improved reliability, and reduced power consumption in electronic devices. The transistor served as a fundamental building block for computers. Just as advances in error correction and hardware in quantum computing are necessary for its reliability and scalability. 2. The Apollo 11 moon landing. 1969. The Apollo 11 mission represents a remarkable achievement in engineering and technology, requiring coordinated advancements across various domains including computing, materials science, and navigation. The success of the mission hinged on rigorous error correction techniques in the spacecraft's guidance systems. Akin to the way quantum computing now demands robust error correction methods to ensure reliable operations. This historical case illustrates the importance of holistic advancements in technology to achieve ambitious goals. 3. The Human Genome Project 1990 to 2003. The Human Genome Project was an international scientific research initiative aimed at mapping all the genes of the human species. This project required extensive computational resources and error correction methods to accurately sequence DNA. The integration of advancements in computational technology parallels the ongoing need for improved error correction and hardware in quantum computing. The successful completion of the Human Genome Project has had significant implications for medicine and biology, similarly to how advancements in quantum computing are expected to impact various fields. Future outlook on quantum computing. The landscape of quantum computing is poised for transformative changes in the coming years. Driven primarily by advancements in error correction and hardware integration. As highlighted by recent developments, particularly the introduction of new four-dimensional 4D geometric error correction codes, the pathway to utility-scale quantum computing is becoming increasingly clear and achievable. Below are key predictions for the future of quantum computing informed by current trends and innovations. 1. Error correction and reliability. The introduction of 4D error correction codes by Microsoft represents a significant leap in mitigating the inherent errors associated with quantum computations. As these codes reduce error rates by a factor of 1,000, we can expect further refinements to error correction techniques that will enhance the reliability of quantum systems. In the next 5 years, we predict that error correction will evolve to the point where quantum computing achieves error rates comparable to classical computing systems, enabling widespread adoption in critical applications. 2. Scalability of quantum systems. Microsoft's integration of 4D codes into its Quantum Development Kit and Azure Quantum Platform suggests a trend towards scalable quantum solutions. As more companies invest in quantum technologies, the development of scalable quantum systems will become essential. We anticipate that by 2030 several organizations will successfully deploy large-scale quantum systems capable of solving complex problems in real time, significantly enhancing fields such as logistics, pharmaceuticals, and cryptography. 3. Real-world applications and industry impact. The practical applications of quantum computing are set to expand dramatically. Current advancements indicate that industries requiring heavy computational power will begin to harness quantum capabilities effectively. By 2030, we predict major breakthroughs in areas like drug discovery, optimization problems, and machine learning, which will not only improve efficiency but also lead to innovative solutions previously deemed impossible with classical systems. 4. Interdisciplinary collaborations. As quantum computing technologies mature, we foresee a surge in interdisciplinary collaborations between academia, industry, and government. Such partnerships are crucial for advancing research and translating theoretical advancements into practical applications. In the next decade, we expect to see numerous joint ventures focused on developing quantum technologies tailored to specific industry needs, fostering innovation and accelerating the transition to utility-scale quantum computing. 5. Increased investment and talent development. The quantum computing sector is attracting significant investment from both the private sector and governments worldwide. This trend will likely continue as the potential of quantum technologies becomes more apparent. By 2028, we predict that investment in quantum research and development will surpass billions of dollars annually, leading to a competitive landscape that fuels rapid innovation. Concurrently, educational institutions will ramp up efforts to develop a skilled workforce proficient in quantum computing, ensuring a steady supply of talent to meet industry demands. 6. Ethical and regulatory considerations. As quantum computing capabilities advance, ethical and regulatory challenges will arise, particularly concerning security and privacy. The potential for quantum computers to break existing cryptographic systems poses significant risks. By 2030, we expect a comprehensive framework of regulations and ethical guidelines to be established that governs the use of quantum technologies, ensuring responsible development and deployment. 7. Integration with classical computing. The future of quantum computing will not exist in isolation but rather in conjunction with classical computing systems. Hybrid models that leverage both quantum and classical technologies will become more prevalent. Within the next 5 years, we anticipate the emergence of advanced quantum classical algorithms that optimize performance across various applications, further blurring the lines between these computing paradigms. 8. Global quantum computing ecosystem. A global ecosystem for quantum computing is likely to materialize, characterized by international collaborations and shared resources. Countries will recognize the strategic importance of quantum technologies, leading to alliances that pool expertise and funding. By 2035, we envision a robust global quantum network facilitating knowledge sharing and accelerating advancements across borders. Conclusion. The future of quantum computing is both promising and complex, with significant advancements expected across various dimensions, including error correction, scalability, applications, and regulatory frameworks. As we approach 2030 and beyond, the momentum generated by current innovations like 4D error correction codes will catalyze a new era of computing. Quantum technologies will not only enhance existing capabilities but also unlock new possibilities, revolutionizing industries and shaping the future of technology.